Right, welcome everyone. I'm going to apologize again. I'm just recovering from a cold, but we're going to do our best to get you guys through this exam prep session. I'm going to get started because we've got a lot of topics to cover in this session. I'm not in the office, so just excuse my background for today. We're going to be covering paper 1, physical science for grade 12 today. We're going to get you guys ready. The topics we're going to be covering look like projectile motion, vertical projectile motion. We're going to be doing momentum and impulse. We will also be covering work, energy, and power. I've left Doppler effect there just in case we have a little bit of time. If we don't have time, I'll skip it out, but it's not that big a topic. I think the mechanics part is going to be the most intense part of the exam that you guys will write. If you guys are joining us for the very first time, very big welcome to you guys. We love having you in the learning space family. I hope you guys join all our webinars going forward. If you're joining on TikTok, give us a big thumbs up. If you're joining us for the first time, if you're joining us for the second or third time and not the first time, please give a quick dancing emoji. Give us a follow as well. We'd really appreciate that. And if you're joining us on Zoom and you haven't followed any of our social pages, go follow our TikTok, go follow our Instagram. Just search at The Learning Space ZA. You can find lots of epic and awesome content. We do lots of little shorts that help break down certain topic and concepts. So as you go through the year, we kind of try and follow the ATP. And then you will find the topics that you're doing at school as and when they come. And you'll meet a lot of our awesome presenters that host some of these live lessons as well. You'll see a lot more faces this year, and it's going to be a really good time, right? Awesome. Those of you that have been in a class with me before, you know very much I like to start a little bit of Q&A. So we're going to jump straight into some multiple choice questions, right? Now, how I want to do these multiple choice questions, I'm going to set some ground rules. I want you guys to engage lots and lots and lots and lots. There's a number of ways of engaging with us on this platform. If you are joining us on Zoom, we've got a Q&A function on the webinar. We also have a chat function on the webinar. Q&A function allows you to ask any questions you might have. Please don't leave questions till the end. Ask your questions as you go. Whenever I find a gap to answer these questions, I will then address them as I do go. Some questions will be answered live. Other questions might just get a typed response, all right? And then if you are in the Q&A and you see that there's a question asked that is similar to your question, there's a function that's called upvoting, right? So don't go and ask the same question someone else asked, just go and upvote that question. It tells me that this is the question that more than one person really needs the answer to. Those are the 2 ways to engage in Zoom. I love lots and lots of interaction. So give me reactions, thumbs up, smileys, fire emojis, post reactions in the chat so that I know that you guys are with me in this lesson, right? The last important thing about what kinds of questions to ask, right? There's different quality of questions. And in sessions like this, where we are very pressed for time, we want really high quality questions. Now, today, I'm going to teach you guys how to ask very high quality questions. So let me give you an example of what's not a high quality question. I don't understand that. Please repeat. What was that? What do you mean? Those are not high quality questions. High quality questions look like, ooh, I understand what you did in step 1 in drawing the free body diagram. What I don't understand is why you gave force applied that angle. That is a very high quality question because it immediately tells me what you understand, what you don't understand, and it allows me to address your misconception directly. And the best part about watching these sessions live and not watching the recording is that I can actually answer your questions live. And remember, if you are going to sit with a misconception and not address it at all, you are going to sit with that misconception forever. But you have an opportunity right now to get one of the best educators in the world from the Learning Space team to actually address your questions now. So please make sure you use that opportunity. That's how to engage with us on Zoom. If you are joining us on TikTok, however, right, you have one way of engaging with us, which is through the TikTok chat. So in the TikTok chat, please just use the chat function to ask your questions, to post your reactions, anything like that. As we go through, you will see I will ask you guys questions, and I want you guys to give me answers before I give you answers. Why I do this? It's because when you are actively learning, right, instead of passively learning, actively learning means you are taking an active role in the learning process. It means I am asking a question, you are thinking about it, you are giving me an answer, you're giving it back. It's a two-way kind of interaction. So active learning works way better than passive learning. If you sit back, you fold your arms, you just watch me do the solutions. That is passive learning. It's not as effective as active learning. So get your hands dirty, do the problems as I'm doing them, right? Even if you think you'll get them wrong, it doesn't matter. You learn everything by getting things wrong. You learn nothing by getting things right. And you learn even less by pretending you were going to know how the answer was going to come just because I've shown you the memo. So please get active, get busy with me. I'll give you guys opportunities to try the questions before I do the solutions, especially the multiple choice questions, right? So to kick us off, I'm going to give us 3 multiple choice questions for you guys to try, just to give us a bit of a test, see how the chat function works and see if everyone's comfortable with them. Hope everyone's good. If you understand the rules or the rules of engagement, please give me a thumbs up emoji, give me a fire emoji, give me a dancing emoji, any emoji that sort of expresses that you are on the right page, you're excited about this lesson. I'll look out for the chat. There's some emojis. Fantastic. Thank you so much. Perfect. So keep throwing those emojis. Then I know you guys are with me on the same page. Let's jump straight in. So here's the very first question for you guys. The question is as follows, right? It says, which one of the following quantities is the tendency of an object to resist a change in its state of motion? The options are going to be A, inertia, B, impulse, C, momentum, or D, acceleration. What I want you guys to do is simply write A, B, C, or D in the chat. That's it. Just give me A, B, C, or D, and then I know what your guys' answers are. I'll open up the chat as well so I can see what answers you guys are giving me. Thanks, Anna, for your answer. Thanks, Rufilwe. Thanks, Dumelo. You guys are awesome for your very quick fingers there. Thanks, Mbonile. You guys are quick there. Okay, I'll give you guys 60 more seconds. Thanks, Lebogang, both of you, the 2 Lebogangs there, for your very quick fingers. Okay, guys, don't feel pressure. Remember, what's more important right now is getting the answer right. So don't feel pressure when someone's answering very quickly. Remember, you've got time, and in the time that's been given to you, use that time. Similar to when you're in an exam, you get given specific pieces of time. One of the things you get given is reading time. Take that time to read through your question. Make sure you understand that question, unpack it for yourself, right? Awesome. We've got 20 seconds left. Thanks, Johara. Thanks, Omokhetswe. 15 seconds to go. What I'm going to do is I'm going to switch my video off just for now, just so that I don't use up too much of your guys' data. All right. And then what we can also do as I'm going through the session, if you are joining us on Zoom and you'd love to ask your question live, put a hand up. And then what we will do is we will give you the opportunity to unmute, right? I know it's a webinar and it doesn't seem like you can engage, but if you put a hand up, we can give you the opportunity to unmute and ask your question live. I like live questions because I can ask counter questions and get a really good understanding of what your challenge is. All right. Thank you for all the questions. Theo, do you have answers coming in on the TikTok there? I don't have it open on my side, but I'll use you as my conduit. Okay, so 5 seconds to go. 4, 3, 2, and 1. All right, which one of the following quantities is the tendency of an object to resist, right, its state of motion? Now, in this case here, right, we are going to have the answer be A, inertia, right? That's what inertia is. It's a tendency of an object. It's a property of mass, right? Of the object, which is essentially the tendency of the object to resist its change to its state of motion. What does that mean essentially? When an object is stationary, it wants to remain stationary. When an object is in motion, it wants to remain in motion. So if you want to change that state of motion, the object is very reluctant, and that's what we call inertia, right? The tendency of an object to resist a change to its state of motion. Okay, it's not impulse, momentum, or acceleration. If you got that answer correct, please put a fire emoji, dancing emoji, any kind of emoji in the chat that shows me you're celebrating it. If you didn't get it right, but you saw where you went wrong, please go and celebrate in the chat as well. Give me a reaction. Awesome. Thank you for all those reactions. You guys are amazing. Let's jump onto our very next question. Okay, the question is as follows, right? Let me just move this chat out of the way so you guys can see. So the question then says, a ball is dropped from red. The ball strikes the floor and bounces vertically up and down on the same spot on the floor. The velocity time graph of the bouncing ball is shown below, with points P, Q, R, and S representing different times during this motion. Ignore the effects of air resistance. Then the question then says, so we see the diagram there, the VT graph shows you those 3 lines, and we see our 4 points P, Q, R, S. The question states, at which time does the ball reach its maximum height after the first upward bounce, right? At which time does the ball reach its maximum height after the first upward bounce? What I want you guys to do is in the chat, put down either P, Q, R, or S. Which time, P, Q, R, or S, does it reach maximum height after the first upward bounce? I'll give you guys 60 seconds for this one. Thanks, Johara. Thanks, Lisho. Thanks, Refilwe, Wamukhetsu, Enna, Komotso Lobuchang. Thanks, Phineas. You guys have very quick fingers there. Thank you for all your guys' answers. If you're still thinking about it, don't worry, take your time. It's very important, right? So you don't want to rush an answer, especially in an exam setting. Rushing an answer to think, oh, I want to get this done with, but then you make a mistake. So pause, think thoroughly through the question. Look at the diagram, VT graph. Okay, what does a VT graph tell me? What does the x-axis represent? What do the lines represent? What do the various points represent? Think that through quite thoroughly, right? I'll give you guys 30 more seconds. Don't rush if you feel pressure to finish. 30 seconds is a long time. Just keep trying, keep trying. It's not like playing the game 30 seconds where it goes by in 10 seconds. This one, my 30 seconds is very generous. So take your time and try and rationalize your answer all the way through. But thank you guys for your answers. You guys are amazing. If you've just joined us or you're joining us on TikTok right now, you missed the beginning. We are busy with a paper 1 June exam prep for grade 12 physical science. We're just doing multiple choice questions. We're going to be covering 3 main mechanics topics. You've got lots of time left. We're going to finish this lesson around 8 o'clock. So there's plenty of time left. Jump right in. There's a question on the screen. Just write down the answer. Give P, Q, R, or S in the chat, please. Okay. I told you guys my 30 seconds is very long. 10 seconds left. Okay. 5, 4, 3, 2, and 1. Okay. Before I give you guys the answer, let's quickly unpack this diagram and see how this diagram is actually set up, right? So when you guys look at this diagram, you will see the following things there. Sorry, let me quickly just minimize these things on my screen. What you guys will see is you've got a ball. So this is the velocity, right? On the y-axis, and we've got time on the x-axis. So the ball starts at a velocity of 0, right? Because we were told that the ball was dropped. Dropped means velocity of 0. They release it, it goes down and starts increasing. It accelerates like in all VPM at 9.8 meters per second downwards, right? So the gradient of this line here, that is going to give us basically G, right? The gravitational acceleration. It starts at 0, it speeds up, speeds up, speeds up, speeds up, speeds up, speeds up until this point here. Notice now, yes, the graph is going up, but the ball is going down, right? Meaning in this particular problem, they chose down as the positive direction. You can already tell that by the information and looking at the graph. So it speeds up, speeds up, speeds up, until now you can see something changes. The gradient of my line is no longer 9.8, right? And because it's no longer 9.8, it's no longer under free fall. So in this point here, at P, I'm not at free fall anymore. What could that mean? It means that my ball has gone from the top and it's now hit the ground for the very first time at P. So that is our first bounce, right? It hits the ground at P. And then you can see now from P going up to Q, I start now with a negative velocity. Remember, if down is positive, negative means I'm now going in the upward direction. So I'm at my fastest in the upward direction at P, and then I slow down until I get to Q. What does that mean? So at the bottom of my motion, I speed up in the upward direction until I slow down and hit my maximum height, apologies, which is my minimum velocity of 0. So I start off at, if this is LMNOP. So if this is point O here, so that means this is point O. I go all the way down to the ground. The ground is going to be point P. Then P, I go all the way up to the top. That is going to be 0 velocity, which is going to be my maximum height. That is point Q. Then we can see from point Q, the ball goes in now the positive direction, which is down. Remember, in this case, it's flipped. Down is positive. So if I'm in the positive direction, I'm now moving down. So from Q, I'm moving down, right? All the way until you can see again what happens. My gradient is no longer 9.8. It becomes something else, which means I'm not in free fall. I've probably hit the ground again. And at that point there, that is R, where I've hit the ground again. And then what we can see beyond that point there, I have a negative velocity. Remember, in this case, negative is up. So I am moving up again until I hit a velocity of 0 again. And that's going to be, apologies for that, until I hit S, which is my maximum height in the second bounce. That's how I now interpret the graph that's been given to the motion of this particular ball. Then they say again, what time does the ball reach its maximum height? After the first upward bounce. And then we can very clearly see, oh, after the first upward bounce, this is the first upward bounce. There's maximum height. What time is that? That's going to be time Q. And we can see that this is our correct answer. So if you guys put Q in the chat as your answer, give yourselves a round of applause, give your guys reactions, fireworks, smiley, dancing, whatever you want to use to celebrate. If you didn't get Q, but you now understand where you went wrong, I want you to guys celebrate as well. Okay, awesome. I'm seeing lots of reactions there. Well done. Lisha's got a question there, right? So isn't P the maximum height? Velocity is 0. Okay, so let's have a look at that, Lisha, right? So when we look at P, we start at 0, we go up. So the velocity at P isn't 0, right? At some point, it momentarily becomes 0, and then it goes up. But we can see here that at P, I have very fast downward velocity, and then instantaneously, in a very small amount of time, I've got a very fast upward. So that tells me I change direction at P. I change velocity at P, right? And it happens very quickly, not gradually, but very quickly, from very high downwards velocity to a very high upwards velocity. Where that happens that quickly, it's when I hit the ground. I hope that makes sense, right? When you hit maximum height, your velocity will not change like drastically from one extreme to the other extreme. It'll change gradually. You'll go from -1, -0.5, 0, half, 1. So what you look at what's happening here at Q, that is more likely a maximum height. So I'm going towards 0, towards 0, towards 0. I'm at 0, then I go slightly above 0, slightly above 0. It's a gradual increase. Whereas if you look at the time, look at this time here, this delta t, it takes quite a while to change from a negative to a positive, right? Which means it was a gradual change in velocity. But at P, look at this. My change in time, it's almost instantaneous, right? It changed so quickly. That is not maximum height. That's when I hit the ground and I come straight back up again. Lisha, I hope that makes sense. If it makes sense, give me a thumbs up in the chat and then I know I can move on. But thank you for your question, because other people probably had the same thought and they didn't ask. But thank you for being brave enough to ask that question. Really appreciate it. Awesome, guys. Let's jump to our third multiple choice question, and then we're going to jump into our topics, right? Okay, the last multiple choice question, just to warm you guys up a little bit, is going to be this one here, right? So it says 2 blocks, P and Q, of masses M1 and M2 respectively, right? I know sometimes we don't do English as a home language. Some people have English as a first additional language. So sometimes it's helpful to explain what some of these things mean, because we can sometimes, we know the content, but then we get messed up by the English. So 2 blocks P and Q have masses of M1 and M2 respectively. What that basically means, whenever they say respectively, it means they would have listed 2 things and then 2 other things. And then respectively means the second set of things belong to the first set of things in the same order. So the respectively just means in the same order. So what that means is that P has mass M1 and then Q has mass M2. So if I say P and Q with masses M1, M2 respectively, it means the order in which I named them and I named the masses, that's the order in which the masses belong to the objects, right? So they're held at rest on a frictionless horizontal floor with a compressed spring between them, as shown below. When the blocks are released and the spring drops to the floor, block Q moves to the right with velocity v. So block Q is going to move this way with velocity v, right? Which one of the following represents the momentum of block P after the blocks are released? Is it A, M1v to the right, B, M2v to the right, C, M1V to the left, or D, M2V to the left? I'll give you guys 3 minutes for this one, because you might need to do a calculation to solve this one properly. Okay, the minute you've done your calculation and you think you know what the answer is, please post the answer in the chat. All I want you guys to post is A, B, C, or D. If you guys have just joined us on Zoom or on TikTok, we are doing a paper 1 exam prep for grade 12 physical science. Welcome, welcome, welcome. If you haven't followed us, please follow us on our TikTok and all our socials at the Learning Spaces ZA. There's a question on the screen. Please attempt it, give us the answer, and then we'll do the solution together. Like I said, passive learning isn't great. Active learning is great. Get your hands dirty. Get it wrong if you must get it wrong. The worst that'll happen is I will give you the right answer. Awesome. Let's get started. I'll give you guys 2 minutes just to finish off this question. Just give me A, B, C, or D in the chat as soon as you've done your calculation. All right, 30 seconds left. If you are still busy, quickly try and get to an answer. 30 seconds to go.
Hi, Ernest. You post your screen.
Hi, Thea. Oh, sorry. Is it paused? It's not showing. Sorry, I don't know what happened. Let me quickly open it up again. See you in the back.
Yes.
Okay. Sorry, I think I was trying to see here how to open my chat and participants so I can see the Q&A. And I think I left the screen and then it paused my screen share because I had to leave what I was sharing. Apologies for that, guys. But thank you, Theo, for picking it up. Okay. 10 seconds to go, guys. 5, 4, 3, 2, 1. If you have not finished your calculation, what I want you guys to do, I'm going to give you extra 10 seconds, guess an answer. So remember, one of the lessons I'm going to give you guys, please note, guys, the things I give you are very useful exam tips. Never leave a multiple choice question blank, right? So sometimes I know some people get scared of multiple choice. They leave it till the last thing, but then you forget to go back and answer it. Remember, even if you're not sure, right, don't leave it blank. If you guess, there's a 25% chance you get it right. If you leave it blank, there's 100% chance you're going to get it wrong, right? So the worst you can do is when they tell you 15 minutes left, 10 minutes left, and you haven't finished your multiple choice, go back and guess some of the answers. Use an educated guess. Try and rule out some of the ones you know are not going to be correct. Or if you have no idea, at least put something. Don't leave it blank. I'm giving you guys 10 seconds. For everyone in the chat, please put an answer in the chat now, even if it's a guess. 5 seconds, go. Put an answer in the chat. There we go. Thank you for those answers that are coming in. Okay, I appreciate it, guys. Remember, that's very, very important. Okay, while we quickly do that, Theo, I'm just going to try and change my screen share from AirPlay to a cable. My screen will go blank for a very short period, then it'll come back on. I think it'll then it'll stop the interruptions where my screen share gets paused when I'm not active. So just give me 2 seconds for me to quickly try and do that. And then tell me if it's fine then, if it still has the same problem. Okay, I'm going to stop my screen share just for a second. And then I'm going to just reshare it with the cable. Okay, here's my screen back.
Yes, it is, Ernest.
Okay. And then when I click away, does it still pause? Does it still stop sharing?
No, it does not.
So you can still see my screen now.
Yes.
Oh, okay, that's perfect. All right, so I want us to quickly then have a look at this question, right? Let's try and break it down a little bit. And we're going to break it down by being able to actually look at the calculation we need to do, right? So when we do this calculation, we've got two objects, M1 and M2, which is the two objects, right? We don't know what their masses are, but they're given to us in terms of M1 and M2, and these are objects P and Q. What we do know is that momentum before must equal momentum after, right? And with that in mind, let's try and figure out what is going to happen. So we're told that there's a spring in between them. The spring will release. When the spring releases and falls to the ground, M2 is going to move at a velocity of V to the right, right? So we know that, let me just write this here, that momentum before equals momentum after. What is the momentum before? It's mv of object P plus mv of object Q. All of this is going to be before, right? So I and I. And then afterwards, we're going to get the m of object P and the velocity after plus the m of object Q and its velocity after. We know that the objects were initially stationary, which means that this is going to be 0 and that's going to be 0. So my momentum before entirely was 0. The momentum after, let's quickly plug our values in. Remember, momentum is a vector, right? So we have to keep in mind our quantities. Let's assume that the right is positive because that's the direction they gave us first. Or you can choose left is positive. It's completely up to you, right? Now, let's quickly go and look at this. So the momentum of object P, right, is the mass of object P, which we know to be m1. The final velocity of object P, we're just going to keep that as velocity of object P final. We don't know what it is, right? Plus, let's look at the momentum of object Q after. The mass of object Q is going to be m2, right? And the velocity of object Q is going to be given as V. We know that this is going to be V in which direction? To the right direction. So we're going to just call that M2V, right? Now they said, what is the momentum of block P after the blocks are released, right? So when we look at this now, we have to then try and say, okay, cool. What represents the momentum of block P? This object here represents the momentum of, apologies, my pencil wasn't working. This here represents the momentum of block P, right? So what is this momentum, right? After it's been released. So we need to make that the subject of the formula and then solve for whatever's left. Okay, so when we take that now, we're going to be looking at this thing. And then as we look at it, what we will then say is, okay, let's take that to one side and take the other units to the other side. So if I keep that on the right-hand side, for example, so I'll keep that as M1 VP F1, which is the momentum of P after, right? It's the momentum of P after. I'll keep that as M1 VP final. And then I can take whatever's left, which is going to be this, to the other side. When I take it to the other side, what you find in that case there, we're going to have a negative M2V. Now, negative M2V, what does that mean, right? So negative m2v, can a mass be negative? No, a mass can't be negative. Mass must always be positive, which means that negative must belong to this velocity. And what does a negative velocity tell us? Remember we said, right, anything to the right is positive, anything to the left must therefore be negative, meaning this is going to then have the velocity to the left. So already we know that the answer, let me quickly do this, cannot be A, cannot be B, because those are all to the right, right? So it must be either C or D. And then which one is it, M1V or M2V? We can see with our final answers clearly M2V, and it's going to be to the left because it's negative, right? So we know it can't be C either, meaning our final answer is going to be D, M2V to the left. If you got that right in the chat, please give yourselves a round of applause and celebration emoji. If not, but you see where you went wrong, go ahead and celebrate as well, because it means when you get to the exam, you're not going to make the same mistake, which is definitely cause for celebration. Awesome. Thanks for the celebration, guys. Let me just check that there aren't any questions in the chat before I move right on. And then we start now with our content part of the session. Theo, I've misplaced my chat. Oh, there it is. Okay, cool. I don't see any questions. Okay, we seem to be good there, and nothing in the Q&A, so we should be fine. Theo, no questions from TikTok. Can I move on?
No questions, Ernest.
Okay, perfect. So, guys, what we're going to do now is we're going to go through a
Ernest,
very brief... Yes, Theo.
a question just popped up now. It says, are they not asking for momentum of P?
Yes, that's correct.
Okay.
So remember, they're asking for the momentum of P. Remember what we were doing now, right? We were saying, let's start with the theory that we know. And don't panic, right? I'm going to go through the momentum theory right now. We'll do a quick summary of the entire topic, and then you'll see how it'll make sense. But essentially, if you follow my thinking there, you start with momentum before equals momentum after. The next step is break down the equation. What does it mean? Momentum before of object one, momentum before of object two equals momentum before of object one plus momentum, momentum after of object one plus momentum after of object two. So that's actually meant to be an F, not an I. Then afterwards, we know that both objects were stationary, right? That's why I said that this becomes zero, that becomes zero, meaning everything on the left becomes zero. On the right-hand side, we know that this represents the momentum of P after. This represents the momentum of Q after. Now, what we need to do is solve for the value of momentum of P after. So this here is momentum of P after, right? What is the value of momentum of P after? It's what's on our left-hand side here. Negative M2V, right? So just because you see M2 doesn't mean it's a momentum, it's the momentum of Q, it's the value of this. So if I took one step further and I just cleaned this up, right? The right-hand side is the momentum of P after, and the value of that is negative M2V, or I can write it slightly better. The P of P after equals M2 negative V, which basically just means M2V to the left. I hope that makes sense for the person who asked that question, but thank you for that question. It's a really good one as well. Okay, perfect. So I love that the questions coming out today are very high quality questions. I'm glad you guys are getting it. All right, let's quickly jump into some theory now, right? So we're going to quickly just do a quick momentum and impulse summary, and then we're going to try a full past paper question for momentum and impulse, right? Okay, so how we're going to go through this now is we will look at the following. So let's start with some definitions, very, very important. So momentum, again, it's a product of an object's mass and its velocity, right? When you think about linear momentum, I want you to remember that linear momentum is a vector quantity, which means it's the same direction, right, as the velocity of the object at the end of the day. And then we're going to then deal with something we call impulse, right? So impulse is a product of your net force acting on an object and and the period of time for which that net force acts on the object, your F net delta T. That is your impulse. We've got a fun little video on our TikTok that'll show you momentum versus impulse and the key differences between those two things there, right? I think I might have a little bit of time to play. It's actually a very short video. Give me 2 seconds to actually try and get it up. And again, I'm showing you guys again why I say it's important to go and follow us on TikTok, because you can then find all this great content that's going to be there. Okay, I'm going to quickly find that video for you. Give me 2 seconds to load it. All right, let me share my screen quickly. Okay, so as I told you guys before, remember our TikTok page is The Learning Space ZA, where you'll find a lot of questions that we do post. Here's a quick video. Hopefully you guys can hear it. Theo, just tell me when the sound
Imagine
does.
rolling a ball. The faster it goes. Imagine rolling a
Can you hear the sound, Theo? Theo, are you there?
Yes, Ernest, I can hear it.
Okay, perfect. I'll play this video. It's a very quick one. It's just a minute.
ball. The faster it goes, or the heavier it is, the harder it is to stop, right? That's momentum, measured as a product of its mass and its velocity. It's kind of like the oomph in motion. Now think of a skateboarder. When they kick the ground, that kick changes how fast they go. That kick is impulse, a quick shove that changes how fast they go, or in other words, it changes the momentum of the object.
Picture two cars crashing.
The force they share changes how they move. That is impulse at work. It's like a high five between objects that changes how they move. Now that was so much fun. So think of momentum and impulse like a dynamic duo. If you want to change something's motion, just give it a little push, or just get it moving in the first place, you know? Rockets launching, soccer kicks, or even catching a frisbee. All of these have a little bit of momentum and impulse magic. So the next time you're playing around, don't forget that you're rocking the science of motion. Imagine rolling a ball. The faster...
Let's answer one. Awesome. So that's a little video. Let me stop sharing and go back to my whiteboard, right? A little video that just gives you a little bit of a hint of what momentum, what impulse is on a high level. Let's quickly go back to my whiteboard and we can finish off looking at the summary, and then we'll do another question, a structured question this time. My screen is just loading. Give me 2 seconds. It's back. Okay. You'll just confirm that you can see my screen.
I can.
Okay, perfect. So we look at momentum and impulse, right? So as your object is moving and it's got velocity, the product of those two things is your momentum, right? But every time you change the momentum, that is going to be your impulse. So a ball is rolling, your friend kicks a ball towards you. That ball is moving with a velocity, it's got a mass. That is momentum in action. And then you kick the ball back to your friend. That kick changes the momentum, right? The mass is still the same, but the velocity is going in the opposite direction. When the velocity changes, you've now changed the momentum. The action of changing momentum is what we refer to as impulse, right? So it's the product of the net force and how long that force acts. So you can give it a big force over a small amount of time, that'll give you big impulse. You can give it a small force, but over a long amount of time, that'll still give you a big impulse, right? So think about it. You can take a ball and you can push it slowly for a minute and it'll go quite far. Or you can kick it very hard for half a second and it'll still go far. That's still giving you both examples of very big impulse, right? Hope that gives you guys a good sense of what momentum is, what impulse is, and how they really differ, okay? Now, let's quickly jump into how to calculate those things, right? So the first thing is when we now calculate momentum and impulse, right? Momentum, as I mentioned before, it's going to be P is M is equal to MV. So P is equal to MV is how we write down momentum. And then when we're dealing with impulse, as I said before, impulse is going to be F net delta T, right? Which is equal in magnitude to the change in your momentum. That's your impulse, right? So you can either write it like this, or you can write impulse like F net delta T is equal to M open bracket VF minus VI. That still works. Okay. Again, note the change in momentum is in the same direction as the force. We can also link momentum to Newton's second law, right? Because we can then say F net delta T is equal to change in momentum over change in time. How do we do that? It's simply by taking this delta t and moving it, dividing both sides by delta t. And then you end up with this. F net delta t is equal to change in momentum over, F net equals change in momentum over change in delta t. And we refer to that as momentum in terms of Newton's second law, right? And that's very important as well. It's another way of looking at it. The net force acting on an object is equal to the rate of change of momentum for that object in that case there, right? Remember, Newton's second law is F net is equal to m times a. Same thing will happen here. If I break this down a little bit, let me show you guys why we really refer to this as momentum in terms of Newton's second law. Delta P over delta T, we said, delta P is going to be m, sorry for that, let me quickly fix that, m times change in velocity, right, over delta T. But hey, wait, what is that? What is change in velocity over change in time? We know that to be acceleration. So that means actually, I can write this thing as mass times acceleration. And if F net equals mass times acceleration, that is exactly Newton's second law. That's why we call this momentum in terms of Newton's second law. That's the equation there, all right? Okay, and then now let's quickly, before we look at impulse and safety systems, right, let's quickly look at the principle of conservation of linear momentum, right? So in an isolated system, the total linear momentum remains constant, very, very important. So what does that mean? It means whatever momentum I had in my system before a collision will be the same momentum I have in my system after a collision. Very, very important, right? So which means the product of the mass and velocity of object A plus product of mass and velocity of object B added together must be the same after the collision. Very important note that velocity is a vector. You must use a sign convention. You saw how it worked out in the previous question as well. So there's a few examples, right, of momentum, conservation of momentum playing out. So scenario number one, it's two objects starting separate, colliding and finishing off separate as well. So we can see initially we've got A and B coming to get towards each other. They collide and then they're moving in opposite directions afterwards. That's scenario one. So they start separate and they end separate. That's one way of writing the momentum equation, right? Then we've got a different scenario. So here's another scenario where the object is starting separate. So A is moving by itself, B is moving by itself, but after the collision, they move off together, right? And then here's how you can write that particular expression, where you've got mv of object A plus mv of object B, that's all initial, equals, after the collision, ma plus mb, so that's the mass of both objects together, times v, because the velocities will be identical. So it's like factoring out that v, and then you get that. That's another way of putting it together, right? And then the last example is the one we did in the multiple choice question, when the objects start together and they end separate. So you're just going to write this back to front, where you have ma plus b times v, and then you basically have mav plus mbv afterwards. Okay, then let's quickly touch on elasticity of collision. So I'm trying to go a little bit fast through this, I do know, because there's a lot that we need to cover. What I want to try and get to as much as possible is us doing the problems. That's how you learn a lot. When we do the problems, get them wrong, and then we panel beat it, just like we did with the multiple choice questions. All right, if there's anything you don't understand, please feel free, put a hand up and then just mention it, and I'll pause and quickly try and address it. Right. I don't have my chat open, but I can quickly bring it back up. Someone asked for the TikTok handle. Theo or someone else in the team, if you don't mind just posting that in the chat, please. It's at the Learning Space ZA. But thank you for that follow. I really appreciate it. And anyone who's on TikTok right now who was following us, I really appreciate that already. Okay, awesome. Now we're going to look at the elasticity of collisions. Now, what does that mean, right? So elastic collisions, when dealing with linear momentum and kinetic energy, they must both remain constant. So a lot of the times you'll deal with just examples where the conservation of linear momentum stands true, where we know that the linear momentum in a closed system remains constant. Momentum before equals momentum after. That's usually the case that always happens in a momentum question. But the kinetic energy isn't always constant. Sometimes that kinetic energy gets transferred into other forms. So now, if you find that the kinetic energy before is equal to kinetic energy after, then you know in that case that the collision is referred to as an elastic collision, when both linear momentum and kinetic energy remain constant before and after a collision. So again, the other question then comes back. Well, then in that case, what does it mean to have an inelastic collision? Well, in this case, an inelastic collision means linear momentum remains constant, but the kinetic energy does not, right? It means your kinetic energy will change. It will either increase if energy was added to my system, or it will decrease if energy was taken out of my system. So if you find that your EK before is not equal to EK after, you are dealing with an inelastic collision. Very important to remember. Again, there, to determine the elasticity of a collision, calculate the sum of the EK of the objects before the collision. And then in a separate calculation, I can't stress this even further, don't equate them as if you're doing momentum before equals momentum after. In a separate calculation, very important, calculate the sum of the EK of the objects after the collision. Then you compare them. So you'll say sum of EK before and then sum of EK after. If they are the same, it's elastic. If they're not the same, it's inelastic. But don't do it as an equation, calculate them separately, and then compare and contrast those particular problems. All right, hope that makes sense, right? And then sometimes they will give you questions that can be a little bit challenging. More and more you'll see them bringing in mechanics topics together, right? Especially if you are an IEB student, you'll always see this happening. DVE students, depending on how they set your papers, some teachers will actually do this to try and stretch and test you guys well. So we call this the use of chapters. Why do we call it chapters? Because the problem will give you multiple steps. So what you'll see is, for example, object A is on a cable, it's on a swing, it swings down to point 2. At point 2, A strikes B, and then B was going to move on. Then point 3, B is going up an incline. So what we can see here, we've got 3 different chapters because 3 things are happening. In number 1, we can see here, there's no collision of objects, right? In this case here, right, we have an object just swinging. So this is going to be like a work, energy, and power. So this is work, energy, and power. We're going to use energy principles to work out that one there, right? So that's going to be an energy principles question. Don't need to worry about that. But 2, we can see what's happening there. There's a collision, right? If there's a collision, anytime you see a collision, think momentum and impulse. So again, there we need to think momentum. There's a collision, right? I always think when you were a child, whenever you see a baby on a bicycle or a child running in a playground, the minute they fall or they collide with the ground, they collide with their friend or collide with a tree, what's the first thing they say? Mama! They call for their mom, right? So when you see a collision, think mom. Mom is going to come into play because mom is the momentum whenever there's a collision. And then finally, there when we look at B, again, no more collisions. It's an object moving up an incline. It changes its velocity. It's probably going to be another energy principles question again. So try and break your questions down so that you know what to use where exactly. You know, sometimes in June exams, some teachers want to, they want to give you a bit of a scare before prelims. They want you to prepare you well. They might give you slightly more challenging questions, or they'll give you a non-routine problem that might involve these things. So note these things. Okay, there's some questions there in the chat. Let me quickly go back in there. Someone's asking me, how do you gain access to the document that you're using? So this is one of our summary notes. So if you are in one of the schools that we support, you would actually have one of our exam prep guides. So our exam prep guides have these notes in them. We're going to start selling them very soon. So hopefully before the end of the year, we'll start selling them. And then you can just go to our website and buy one of these books, which has these notes in there, right? For now, you can't necessarily get it unless you're a school that we support directly, but we're going to get them on the shelves very, very soon. But thank you for your interest. And then someone against there, may you please explain when we use scenario, the Newton's second law of momentum? Okay, so basically, I'm going to try and see if I understand your question. I'm assuming it's a TikTok question. Explain when we use the momentum in terms of Newton's second law, right? So again, oftentimes look at what information you've been given, right? And look at what you've been asked to solve in a particular case. So sometimes they might ask you for you to go and work out the acceleration of an object, but you're dealing with a momentum thing. You can then bring that back because now I need to somehow bring acceleration into play. Or they'll say, please work out the net force. In that case, F net equals delta P over delta T. You can find change of momentum. It might have been something that was done in a previous question. Take delta P straight in over delta T. That version of the equation might just work. So look at the information that was given to you and then look at what you need to give out at the end of the day. That's also going to be pretty useful. Okay, so that's my quick summary. I know it was quick and I apologize for that, but it's because I want to get to the problems so that we can do those problems well together. Awesome, guys. So let's look at this question now. So question 4 is the one that we're looking at right now. So question 4 is going to be as follows, right? Question 4 then says, trolley A of mass 7.2 kilograms moves to the right at 0.4 meters per second in a straight line on a horizontal floor. It collides with a stationary trolley B of mass 5.3 kilograms. After the collision, the trolleys lock together and move to the right. So you can see the scenario that's here. Start separate, move off together, as shown in the diagram. Ignore any frictional effects. 4.1 states the principle of conservation of linear momentum in words. Okay, I'll give you guys very, very, very quick 30 seconds to put that down. Remember, I said you must have paper. We're doing this question together. Quickly write down the principle of conservation of linear momentum in words. You can put it in the chat. You can put it on your piece of paper. On the chat is even better, then we can share our answers. I'll give you guys 30 seconds to type that up, and then we can quickly look at the correct answer together. Give you guys 30 seconds. Go for it. Thank you, Anonymous, for posting that in the Q&A. I'll wait for other answers in the Okay, let's quickly jump in there and look at what the actual answer is. Yeah, there we go. There's answers that came through the chat. Thank you guys so much. We've got thanks to Melo, Lebogang, Wamuketswe, and someone from TikTok as well posted an answer. Thank you guys so much. You guys are awesome. So the answer is that in an isolated system, the total linear momentum is conserved, or you can say in an isolated system, the total linear momentum remains constant, right? Let's quickly put that together. Quickly write that there. So the total linear momentum in an isolated system remains constant or is conserved, right? Or you can say remains constant. You don't have to write both. One of them will be fine. Awesome. If you got that right, give yourself awesome celebration in the chat, reactions, wherever it is. Thank you so much. I see them coming through there. If you didn't get it, but you now see what the definition is and you know you'll get it in your June exam, definitely give me those reactions. I love to see them, right? Nice, easy one to start off. Then let's look at the next one, right? 4.2 says, calculate the magnitude of the velocity of the trolleys immediately after the collision. So that's the first one. 4.4, 4.2.1. Calculate the magnitude of the velocity of the trolleys immediately after the collision, right? So in this case here, remember, we're going to use the conservation of linear momentum. They'll always give you these kinds of things, right? Where they kind of give you the answer or the way to answer. So notice how 4.1 says, state the principle of conservation of linear momentum. The next question then says, calculate something, something, something. And usually when they ask you for a definition, the next question requires you to use that law or that definition to calculate that answer. So they were literally giving us those 5 marks for free, as long as you knew your definition, right? So let's quickly jump in and do that for 4.2.1. So as we do it, we say momentum before equals momentum after, right? So my P before, or the sum of my momentum before, equals the sum of my momentum after. What does that look like? Momentum before, I've got momentum of object A, momentum of object B, and then I've also got momentum of them together afterwards. So let's quickly write that down. So I'm going to have the mass of A times the velocity of A initially, plus the mass of B times the velocity of B initially, and that needs to equal the mass of A, remember they're together, plus the mass of B, put that all nicely together in brackets, times the velocity of them both finally, right? There's our equation. That's the hardest part. The easy part now is substituting values that they've already given us. So let's quickly go do that and sub the values they've already given us. So let's quickly go look up. The mass of A, we were given there at 7.2. Its velocity was 0.4. The one thing we need to remember again, momentum is a vector. So let's pick a sign convention. I'll pick right as positive and left as negative. Let's go fill that in. So momentum of, the mass of A, we said now we saw was 7.2 kilograms. The velocity of A was 0.4, right? And it's moving to the right, so it's a positive 0.4, right? Plus, let's find the mass of B and the velocity of B. The mass of B, we can see there's 5.2, right? And then were we given the velocity of B? Let's quickly look. It's not in the diagram, but if we look at the question, it then says it collides with a stationary trolley B. What does stationary mean? Stationary means the velocity is 0. It wasn't moving in the first place. Okay, let's quickly go substitute that one in. Apologies for that. So let's quickly do that. We saw the mass is 5.3. Let's substitute that in. So we know our mass of B is 5.3. And then the velocity in that case there is going to be 0. All right, we've put the things that we need. And then afterwards, let's put those masses. The mass of A, we know that 7.2. Plus the mass of B is 5.3 times the final velocity. Now what you guys have to do is make VF the subject of the formula and find the final answer. So I won't do the math in between. I'll leave that for you to do and post your answers in the chat. I'll give you guys 2 minutes to quickly give me that answer. Thank you for the quick fingers there. We'll give you guys more time to enter the answers you've got. Thank you, Mike. Thanks, Palisa. Thanks, Dumelo. Thanks, Anna. Thanks, Dumelo. Thanks, Lebogang. Thanks, Dimpo. Okay, 10 seconds for those that are not done. 5, 4, 3, thanks, Johara, 2, and 1. Awesome. So if you got a final answer of 0.23 meters per second, right? Well done for that. I know some of you guys put the direction as well. I didn't put the direction, but it's only because they asked me for the magnitude and they didn't say calculate the velocity. So if they say calculate the velocity, remember, velocity is a vector. So you need to give magnitude, units, and direction. If they say calculate the magnitude of, then you only need to give the magnitude and the units. If you give the direction, there's nothing wrong with that, right? They won't mark you down for that. So sometimes it's good to just put it all together. For those that did, well done to you guys. But in this case, if you just gave the magnitude and the units, that's very important, and left the direction, then that's still okay as well. Awesome, guys. Hope that makes sense to you guys. Let's jump and do the last bit of this question here. 4.2.2 then says, calculate the magnitude of the average net force exerted by trolley A on trolley B during the collision, if the collision time is 0.02 seconds, right? So they want the average net force. And the reason why they say the average net force, it's because remember, a collision happens over time. The force is going to start a little bit soft. It's going to go a little bit harder, and it's going to get soft again. as the objects deform and they hit each other. So the average net force says, assume the force happens like boom once. What does that force look like if it was a constant force that happens in that case there? So when they're asking us about the force of a collision, we need to think impulse, 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 right? Momentum is that object moving with its velocity and its mass. Impulse is whenever the momentum changes. If it slows down or speeds up, then there was a force that made me do that, right? Think back to Newton's second law, right? That when a net force is applied to an object, the object will accelerate. Acceleration means I'm changing my velocity. If I change the velocity, I'm changing my momentum as well. That's very, very important. Okay, let's do 4.2.2 together. So 4.2.2, they want the average force exerted by this trolley, trolley A on trolley B during the collision, if the collision time is 0.02 seconds. So we're going to then use our impulse calculation there, where we know that impulse F net delta T equals change in C, right? Now we've got that there. We can quickly expand this a little bit more and then try and make sure we've got all the values we require. So F net delta T equals, what is change in P? It's our change in momentum. It's mass times change in velocity. That's going to be the mass, right? With VF minus VI, right? Now, I want to ask you guys a question quickly. So we've got that equation. F net delta T, that's fine, VF VI. Are we going to use object A or object B to solve this problem? Quickly post that in the chat. They said, find the average net force exerted by trolley A on trolley B during the collision if the collision time is 0.02. Are we using trolley A or trolley B? Thanks, Palisa, for your answer. I don't know who the other person is. I just see 2 dots. Thank you for your answer as well, right? There's 2 answers in. If you're not sure, you can guess. And if you think it doesn't matter, you can also write it doesn't matter. Or write all of the above. Or not all, but rather any of the above. Thanks, Zeliwe, for your answer. Thanks, Akum. Thanks, Lebogang. Thank you, Fola, for your answer. Thanks, Johara. Okay, awesome. So I've got mixed answers in the chat. Some are saying A, some are saying B, all right? So in this case here, the average net force exerted by trolley A on trolley B during the collision. So if the collision time is 0.02 seconds. So the actual answer is it doesn't matter. Why do I say it doesn't matter? It's because remember, Newton's third law states that when object A applies a force onto object B applies a force of equal magnitude in the opposite direction back onto object A. So the value of that net force, the magnitude of the net force, will be exactly the same. That's very important. If they wanted the force in total, including the direction, that's when it matters, because depending what value you put, that tells you what direction the force is, right? So if we were looking for exerted by trolley A on trolley B, which is going to be a force in the right direction, right? You're going to basically then say, I'm going to use trolley A to find that value if I needed it to be correct to the direction. And then I'll get an answer that's going to be positive, which means it's going to be a force to the right. If it's trolley B on trolley A, I would use trolley B's. If it's trolley B's force, I'll use trolley B's values. But because it's trolley A's force, I'm going to use trolley A's values. But it doesn't matter. You can do it both ways and you'll see the answer will be exactly the same. Okay, let's quickly try and do this one together. F net delta T is equal to M VF minus VI. We don't know what our F net is. That's what we're trying to find, right? Delta T was given to us as 0.2 seconds. We could use a different color. 0.02 seconds. The mass in this case, I'm going to use the mass of trolley A, which is 7.2. Trolley A's final velocity, the final velocity we worked out in the previous question, the 0.23. That's the final velocity for all of the trolleys, right? So that's going to be 0.23 minus VI, which is the initial velocity. The initial velocity of trolley A is going to be 0.4. And then you can take that and plug it into your calculator, right? When you take that and plug it into your calculator, what you guys will see there is you will then end up with the F net of, if you keep it there, it's going to be negative 61.2 newtons. What does that negative mean? The negative means the force is acting to the left. So we can see here, by plugging in trolley A, right, we then see the force that trolley A experiences in this case here, right? So that's going to be F net equals 61.2 newtons to the left. That is what trolley A experiences. That's what A experiences. Meaning the final value that we're actually looking for is going to be 61, sorry for that weird one, 61.2 newtons to the right. We don't even need a direction because they asked for the magnitude to the right, which is what trolley A now applies to object B. I hope that makes sense to you guys. What's most important is this magnitude, because the question said, please give the magnitude of the average net force. So you can use either of them, and then depending on the direction that you get out. So in this case, we got a negative answer, meaning that's what object A experiences, which is the force of B on A. We then know, well, it'll be the same magnitude force, just that A will apply it to the right. And then in that case, we just needed the magnitude anyway. So we can just plug that in there. Hope that makes sense to you guys. That is momentum and impulse in a nutshell. All right, we're going to move on to another topic just briefly. If you guys have any questions, please post them in the chat. I'll give you guys 2 minutes for a little bit of a Q&A if you guys need. All right. Theo, you'll just share any TikTok questions or comments that come up. But I'll give it 2 minutes while I change over to my next topic. Okay, perfect. I don't see any further questions. I'm going to move on, right? Oh, wait, there is a question there. So if we use B, we get a direction of right, 100%, right? So if you would use the values of B, you'll get the same magnitude, 61.2, but except it'll be a positive answer. But the key thing, it doesn't matter in this case because they wanted the magnitude, which is the most important thing. So whether you use A or B, it doesn't matter. You'll get the exact same answer in terms of the magnitude of the force you experience. All right. Okay. All right, that's momentum and impulse in a nutshell. I think the question we did before, as well as these two questions, give us a little bit of experience with trying to do momentum and impulse, as well as impulse in that case then. Let's quickly jump onto our next topic. Give me 2 seconds to get us there. And boom, okay, so we're there. So the next topic we're going to cover is going to be work, energy, and power, right? So now, when dealing with work, energy, and power, sorry, someone does have another question there. So sorry for this, but do you do private lessons? Yeah, Fola, we do at the Learning Space, we do offer private lessons, 100%. So just go to our website, www.thelearningspace.co.za. One of the guys in admin will post that in the chat shortly, and then you can just try and engage with us in that particular case, right? We've got a lot of awesome tutors. If you've been watching any of our other lessons, I think we've got a grade 10 lesson happening at the same time right now. That's also doing grade 10. So we do cover quite a lot of stuff. So you can just check it out, the Learning Space.co.za, and then you can try and engage with one of our tutors there. Thank you for that question. Okay. Work, energy, and power. Let's look at this, right? So I'm going to quickly give you a very high level overview of work, energy, and power, right? So let's start off with energy, right? So in GET, right? So before grade 10, you would have learned that energy is the ability to do work, right? So they'll tell you, without any energy, you can't do any work. If you come to class without having eaten, you've got no energy and you can't do work as a result, right? So, and then the question then comes, well, okay, I get what energy is, but then what is work, right? And then the description we always get of work is going to be the following. They will always give us this definition and say, work is done by a force acting over a distance. So they'll say, work applied over a particular distance, if the force is perpendicular, not perpendicular, in the same direction as that particular displacement. Now, I get that as a definition, it's what is required of us, but it doesn't really tell us what work is, right? So what I want you guys to try and take this, not as a definition, but take this as a way to help you understand what work is. So if energy is the ability to do work, work is going to be the transfer of energy. I know it sounds, some people will call that circular reasoning, right? Meaning I'm using one to describe the other, but let me try to break it down for you guys. So doing work is the Hi, Theo.
Someone from TikTok is asking if you can please do graph questions as well.
For work, energy, and power.
Yes.
Or for vertical motion. Okay, I'll see if the question I've got has got graphs in it. If not, I know for a fact on our TikTok, if you scroll to any time we did work, energy, and power, you'll find graph questions. Just search for the learning space, work, energy, and power. You'll find us doing graph questions there for sure. I know I've done graph questions on TikTok if I don't get time to do them today. But thank you very much for that. So yeah, you can find lots of videos, guys, of us doing lots of topics on TikTok as well as our YouTube. We've also got a YouTube, also the learning space. So YouTube, someone just asked as I was saying it, are you on YouTube? So yes, we are. So if you go to youtube.com/the learning space ZA or at the learning space ZA, you'll find lessons that we've done as well for exam preparation before in that case. So going back to, yes, Theo.
The question was for momentum and impulse.
Momentum and impulse. So yes. We'll have momentum and impulse questions there as well. Definitely, if you go back and look for our lesson recordings, you'll find lesson recordings we did previously. So I'm pretty sure work, energy, power, I was very sure. Momentum and impulse, I'm not 100% sure. But if they can share a question with me somewhere through our social, send me a DM with the question you'd like me to treat, and we'll do a video of it for you. For sure. Okay. So coming back to work, energy, and power, right? So again, energy is the ability to do work. Work is the transfer of energy, right? So the transfer of energy, what do I mean by that? So remember, if I don't have energy, I can't transfer any energy. That's why it's called energy is the ability to do work. If doing work is transferring energy, without energy, I can't give you energy. Imagine when you're tired and your friend comes and they want to tell jokes and all of those things, and you are so tired, you can't engage them, you can't give their conversation energy. So think about how we transfer energy, right? If you push a car, you need to have energy to give that car kinetic energy. So work is the process by which we transfer energy from one form into the other. All right. So positive work is when energy is transferred to the object by the force. Negative work is when energy is removed from the object by a force. All right. So the equation for work, W is equal to F delta X cos theta, where F is the force doing the work, delta X is the displacement of the object, right? And then cos theta is the angle between the force and the displacement. Don't confuse this with the angle of the incline. Very, very important. Okay. So here's some examples. Here's example number one. There we see this block, 10 Newton force, and it moves 5 meters. So we know that F is going to be 10, delta X is 5, and cos of 0. Why cos of 0? What's the angle between this line and that line? It's 0. There's nothing between them, right? Second example, you've got the force acting at 30 degrees. The displacement is this way. So you can see the angle between the displacement and the force is 30 degrees. So you'll have a force of 10, delta X of 5, and cos 30. All right? Then we see an example now, number 4, this one here, right? Example number 4, we've got still 10 newtons acting up. The object moves to the right, right? So it's like, for example, if that was our normal force and the object's moving to the right, remember we always say normal force doesn't do work. Why does it not do work? Because normal force is always perpendicular to the motion. Where our force is 10, our displacement is 5, but it's cos of 90 because there's a 90-degree angle between my force and my displacement. And cos of 90 is 0, meaning any force that is perpendicular to my motion will do 0 work. Very, very important. Then we're going to be looking again, final scenario here. We've got a force acting opposite the direction of motion. So that is going to be an angle of 180 degrees. Do you see that, right? So in that case there, we've got F is 10, delta X is 5, and then our cos 180 is -1. That's why this is going to be -50 joules. 10 times 5 is 50, times -1 will give you -50 joules. It's a very important thing. It seems very simple, but when you are applying this, it's going to help you save a lot of mistakes by knowing how to apply your work calculation, right? Especially when we get to the more complex work energy theorems and the work non-conservative. This is the foundation of that. All right. Now, with that then, let's look at how do we calculate net work, right? So net work, we simply add all the work done by the forces together. Step 1, I'm going to even call this step 0. So the first step is draw a free body diagram and determine which forces will do work, right? So let's imagine here we've got an object. I'll draw a fictional object there, free body diagram. We will have F of gravity, right? Let's say we've got an applied force, right? This way. Let's say we've got coming backwards a force of friction, and then going upwards. Going upwards, we've got a force normal. Or let me not put it that way. Let's say this object is on an incline. Let me see if this is going to let me do what I want to do. So I'm just going to quickly circle this. Okay, let's imagine this is an object on an incline, in which case my FG is not like that. My FG is like this. And my F normal is then like that, all right? Now, as we look at this, let's say, okay, which forces will do work? So force of friction, that's going to be cos 180. It's going to do work. Force of gravity, it'll be cos of 100, and let's say cos of 200 or something. It'll do work. Force applied, cos of 0. It'll do work. Force normal, cos of 90. Cos 90 doesn't do work because it gives you 0. So in this case here, we can see 3 of my forces do work. F normal doesn't do work. And in that case, we can then take those and put them into our W net equation. So W net is the sum of all the work on my object. So it's the work due to my F applied, which is that one there. It's the work due to friction, that one there. It's the work due to gravity, that one there. And when you add them all together, you will then get them together. So here, what you can do, option 1, is say W net is equal to F net delta X cos theta. So you can work out an F net of those 3, or just work out all the work individually. F delta X cos theta for all of the individual forces and add them together. All right. Another way to do it is to use the work energy theorem as well. Find the change in kinetic energy, and that will give you the net work. So those things will really help you to calculate net work done. Use work energy theorem when the velocity values are given, or you ask to find VI or VF. That's going to be very important there. Okay. Now, in that case there, let's quickly have a look at work done by gravity, right? Work done by gravity can happen in 2 ways, especially because we always tend to find inclined plane questions that require us to then work with FG perpendicular, FG parallel, right? So if an object goes up, then WG is negative. If an object goes down, then WG is positive. What does that mean? An object that goes up, the work done by gravity is negative. It's negative work, right? When you go up, gravity makes it harder for you to go up. Gravity takes energy out of your system. Throw a ball up, what's going to happen? The kinetic energy is going to go down to 0 because gravity is taking energy out of my system. But if you throw a ball down, WG, work done by gravity, is positive. Because if I drop a ball, it'll increase kinetic energy. Why is that happening? Because gravity is adding energy to my system. So when an object goes up, work done by gravity is negative. When an object comes down, work done by gravity is positive. Okay, so we can see the work done by gravity for an object that goes from 5 meters down to 0, all right? We see in this case here, we're going to gain 98 joules as we do that. And then let's look at an object on a slope, right? So an object on a slope, what we can do there, we'll see from a 2 kg object going from the bottom all the way up to the top, like that there. We can do object, first case there, find FG parallel, so FG sine 30. Once you've done that, you can then use that to find work done by gravity, where you use FG parallel and your delta X becomes your slope length. That's one way of doing it, right? If you've given that. There's another way of doing the same problem, right? If, however, you were not given the slope length, but you knew the height that this object was going to go through, then you know that the work done by gravity, right, is going to be equal to FG, not FG parallel, straight FG times that height that it goes up. And then cos theta depends if it goes up or down. If it goes up, it's cos 180. If it's coming down, cos of 0. And then you determine whether you're going to get positive or negative work. So you can either use FG directly if you use the height, or use FG parallel if you're going to use the slope length. Very, very important. Okay. Then quickly, let's come back down to conservative and non-conservative forces, right? So the work done by a conservative force, the work done by conservative forces is independent of the path taken, i.e. it doesn't matter what path the object took to get from A to B. So imagine now we've got this object, 2 kg object from there down to here, right? The work done by gravity in this case, right, is the same in the following two scenarios, whether it goes straight down or it takes a very scenic route down. Because what is the most important thing? The most important thing is the displacement. And in this case, because gravity works vertically, the vertical displacement is the most important thing in that case there. All right. So independent of the path taken, that's what we refer to as a conservative force. To give you a cheat sheet in this case here, right, the only conservative force you will deal with from a CAPS perspective is going to be gravity. Other examples of conservative forces is like a spring force. A spring force is a conservative force as well. So conservative forces are forces that will give you, that will be positive in one direction, but negative in another direction. That's another way of also looking at conservative forces, right? Work done by a non-conservative force depends on the path taken. Example, work done by friction will differ in the below scenarios. So friction will be something here, but it'll be maybe more here because the path of the second one is longer. The longer you move, the more friction will take out of my system. Very, very important. Then we can actually come down to the point of remembering that we use this equation of WNC, work non-conservative, and the work non-conservative is equal to change in EK plus change in EP. Now, this is important because if you think back to mechanical energy, which you'll see now, the conservation of mechanical energy in a conservative system, meaning a system where you only have conservative forces. So for your case, in CAPS, the only conservative force is gravity. In a system where you only have gravity as the force acting, you have a conservative system, and the mechanical energy there is conserved. Meaning your total mechanical energy, your EP plus EK will remain the same. You will have no change in EK plus EP together, right? But if it's a non-conservative system, you will have a change in EK plus a change in EP together in that case there. Then we look at mechanical energy quickly as we wrap this up, right? So when looking at mechanical energy, we then say EMAC is equal to the sum of my EP plus my EK. That's going to be mgh plus my half mv squared. The principle of conservation of mechanical energy is that in an isolated system or conservative system, the mechanical energy remains constant, right? So at maximum height, EP is at a max and EK is at a minimum, meaning your maximum height has velocity of 0. At maximum speed, EP is at a minimum, right? And EK is at a maximum. So your height is going to be relatively 0. So depending where your reference point is, that'll be the lowest height you will reach and the maximum speed at that point there. And then we can use this equation here in an isolated system where there's a vertical displacement where you have E mech before equals E mech after. And if that doesn't work and the system is not conservative, you are going to use the work energy theorem, or you will use work non-conservative, right? So work energy theorem is W net is equal to change in EK. We saw that up here, work energy theorem, or you can use work non-conservative. WNC is equal to change in EK plus change in EP. Okay, I'll pause to see if there's any questions. And if not, I'm going to jump straight into the question for this topic. Okay, I don't see any questions. Okay, let's jump right in to the question for this topic. So in this question now here, what we can see, we've got the following question. So the question is question 5. It says, an electric motor pulls a 20 kg crate from rest at point A up an inclined plane by means of a light inextensible rope. The inclined plane makes an angle of 18 degrees with the horizontal. B, C, and D are points on the inclined plane, and the distance between points A and C are 15.6 meters, as shown in the diagram below. Then what we're going to do then is we see the diagram that they've given us. Hi, Thea. Who was talking? Can you guys hear me? Sorry. See, I don't know if you were talking or someone else was talking. I was hearing someone, maybe I was just hearing myself. Sorry. I think my flu is giving me hallucinations, guys. Sorry about that. So we see this diagram there. No, I think maybe someone unmuted who was listening to the session, and my voice came back because I heard someone talk, and then I think it was myself echoing. Okay, so we've got the 20 kg object at the bottom. It goes up an incline, being pulled by an electric motor, as we can see. The distance between A and C is 15.6 meters, and that's a rope that's pulling it up. Then we're told there that the motor exerts a constant force of 96.8 newtons parallel to the inclined plane. So meaning we have an angle of 0 between the rope and the plane, right? A constant frictional force of 13.5 newtons acts on the crate as it moves up the inclined plane. Very, very important there for us to note. All right, now that we've got that there, it says define a non-conservative force, right? We just looked at that together, right? What is a non-conservative force? A non-conservative force is, a force is non-conservative, right? It's the work it does or the work done on the object by that force, right? When it's moving between 2 points is dependent on the path taken. Let's quickly put that down. So a force is non-conservative. If the work it does is dependent on the path taken. Okay, if you can't read my ugly handwriting, we can quickly go back up to our notes. There, the work done by a non-conservative force depends on the path taken, meaning a force is non-conservative if the work it does on an object does depend on the path taken. Hope that makes sense to you guys right there. Let's quickly come back and do the next part of the question. 5.2, use energy principles to calculate the speed of the crate when it reaches point C. So they want us to then use energy principles to calculate the speed when this crate reaches point C. Let's first start by looking at key facts and figures. So we're given the mass of this object, right? We're told that this object is pulled from rest. There, very important, meaning the velocity at A is 0, right? And this electric motor is going to pull it up. Angle of 18 degrees up the incline, the horizontal, that the distance is that there. Okay, cool. And then we're told that the motor exerts a constant force of 96.8 newtons. Let's also highlight that, which is very important. And then we've got a constant frictional force of 13.5 newtons. The first thing I want to do in this case is I'm going to draw a free body diagram. They didn't ask us to do it, but in any mechanics question, I always say, always draw a free body diagram. It's super important. So let's start by drawing a free body diagram. Let me just give myself a page to work here, 5.2. Okay, so 5.2, we're going to draw a dot to represent that object, and that object will have a force vertically downwards. That is going to become our weight or our FG, right? We were told there's a constant frictional force acting, apologies for that. There's a constant frictional force acting down at a particular angle like that. That's my force of friction. Let's make my dot a little bit bigger because now my diagram looks weird. And then there's a force going upwards, right? And make sure that this force applied, or the force of the electric motor, it's going to be longer than our frictional force, right? Because we were told that frictional force is 13, but our constant motor force is 96. So that force must be bigger in your diagram. And then you'll also have a normal force which acts perpendicular to your surface like that. That's our force normal, right? And then again, just to remind ourselves which forces do work and which forces do not do work, we know that my force of friction will do work, my FG will do work, my F applied will do work, but my force normal will not do work because it's perpendicular to the motion of my object. Now that I've got that there, we were asked to quickly use energy principles to calculate the speed of the crate when it reaches point C. Now, first of all, the question I always ask myself, is this a conservative system? Meaning, do I have gravity and gravity only acting? If that's the case, I'm going to use conservation of mechanical energy. But I don't. I've got an electric motor that's applying a force, non-conservative. I've got friction, non-conservative. So this is a non-conservative system, right? And they want me to find the speed. Another hint, speed. Which calculation involves velocity? Remember, work energy theorem. Change in EK is going to, W net is equal to change in EK. That's where speed comes into play. So whenever we do that, we're going to think, okay, non-conservative system that requires us to work with speed, work energy theorem. So in this case here, we're going to use our work energy theorem to say W net is equal to my change in EK. What is W net? Remember what I said before. You're going to take that force, find the work. That force, find the work. That force, find the work, and make it equal to our change in EK. Let's quickly put that together. So we're going to find the work done. Sorry, apologies for that. I'm going to find my work done by gravity, plus I need my work done by my applied force, right? Plus I need my work done by friction. And all of that is going to be equal to change in EK, right? Which is going to be half m vf squared minus vi squared. All right, please don't make the mistake of writing this. Sometimes I see when you mark papers, people do this. They'll say vf minus vi squared. Please note that is incorrect, right? It's vf squared minus vi squared. That's the correct way of doing it. Okay, now that we've got those there, let's expand everything else a little bit further, right? So we're going to substitute work done by gravity, substitute work done by a force applied, substitute work done by friction. Okay, so work done by gravity, let's see what we can use there, right? In this case, we don't have a height for C. If we had a height, we were going to use FG and the vertical height. We don't have that. We only have the slope length, meaning I have to now use FG parallel, right? FG sine theta, very, very important. And then for my force of friction, that's fine. It's acting opposite my motion. That's going to be cos 180. For my force of the electric motor, that's going to be cos of 0. We've got those values there. We can substitute all of those things in and work it out. Okay, let's quickly jump in and put the values in. So work done by gravity. There we need Fg sine theta. That's our force. Our delta x, we know it's going to be the delta x, which is the slope length, times cos of gravity. Fg parallel is working against my slope. That's going to be cos of 180, right? Work of the applied force, that's going to be the force applied, which is for the electric motor, times the same delta x we've got there, times cos of 0, which is acting in the same line of action. Work done by friction, right? So it's going to be the force of friction times my delta x. Friction is acting against my motion. That's going to be cos of 180. So you put all of those together, and that must be equal to half mvf squared minus vi squared. So it's going to be half my mass into vf squared minus vi squared. Very, very long equation, but if you follow your process, you'll get to the right answer. Let's substitute the values now that we've got, okay? My Fg, we were given a mass of 20, I think it was 20. Yes, given a mass of 20 kgs. So Fg sine theta, Fg is going to be 20 times 9,8. That's my Fg sine theta. In this case, it's the theta of the angle of the slope, right? Our slope was given at 18 degrees over there. So Fg sine 18, very, very important. Okay, in that case, the sine of 18. Our delta x we were given, this is our delta x here, that's 15.6 meters. That's delta x. So we're going to substitute that delta x in there. 0.6 meters, and then cos 180 remains. Cos of 180. Okay, that's the first part. Plus my force applied. We were told what that force is, that 96.8. We will put that in there. So we've got 96.8 newtons. Let me fix that 8 quickly. 8 newtons times my delta x, that's 15.6. Right? Times the cos of 0. Cos of 0 is just 1, which is fine. We can just leave it there. Okay. Plus my force of friction. We were given the value for friction. It is 13.5 newtons. Let's substitute that in there. So force of friction will be 13.5 newtons times delta x, that's 15.6. Sorry for that. 15.6 times cos 180. Okay, and that's equal to half mv f squared minus vi squared. Half remains just a half. The mass was given as 20. And then here we've got vf squared. That's what they need us to find, right? Vf squared minus vi squared. Vi is just going to be 0. So it's going to be just 0 squared. So that's basically just going to be half 20 vf squared. So if you take all of that, I hope it's going to be visible to you guys, the very long equation, right? Take all of that and plug it in. So essentially you're going to have on the right-hand side, let me write it bigger, half of 20 is 10 times vf squared, because it's minus 0. And everything on the right-hand side then needs to come together and then become a particular value. When you plug all of that in your calculator, you'll end up with a particular value. Divide that value by 10 and then square root, right? Just for the sake of time, I won't do the maths in between, but I will tell you what the final answer is. If you've got the final answer already, right, you can plug it into the chat, but I'll give you guys the final answer in this case. So you will then take everything on the left, remember, divide it by 10 and then square root that answer, and you should have a final answer of VF is equal to 5.96 meters per second. We will put the recording of this lesson on YouTube, so you can always go back and watch it at your leisure and pause where you want to pause. Doesn't mean you must leave the lesson, because then you don't get chances to ask questions, right? Okay, that's going to be the value for your VF in that case there, 5.96 meters per second. I hope you guys got that answer. If not, don't panic. Just spend some time practicing these problems, especially because we had a very long equation to solve there, right? Let me quickly see some questions in the chat there. Someone said there, can you use the non-conservative formula where you calculate the height from C to the ground using trig ratio? So yeah, definitely in this case you could have used so the not WNC. You could have used WNC. It's just going to be a little bit of a long way around, but it definitely will work. And then the other thing you could have used, so when they're saying using trig, so what they're saying is, if I imagine this triangle here, right, it's a triangle. If I take a line from C straight down, right, that becomes a right angle there. And we've got a right angle triangle where we know that this is 15.6, that is 18 degrees, and we can use trig to find the height, h. And then in that case, you can then just use FG and that's h. It's extra steps. I wouldn't do it because it gives me more places to get things wrong, but you're more than welcome to try it if it's more comfortable for you. And then using WNC is going to work exactly the same way, right? Because in that case there, you'll just use, let me show you guys what I mean by that. So if you look at WNC is the following. Work non-conservative is equal to change in EK plus change in EP. Think about change in EP. Change in potential energy, right, is going to be mg h final minus h initial, right? That looks very similar to work done by gravity. Why do I say that? Work done by gravity is going to be the force of gravity times your delta x, or delta y in this case, because you're working vertically. So that's going to be change in height. So force of gravity is mg. Your change in y is going to be your final height minus your initial height. So in that case there, you'll have those particular differences in that case there. And then because of the same, so if I move my change in EP over to the other side. So I've got work due to non-conservative forces. What is work non-conservative? Work non-conservative is work done by my force applied. It's also work done by my force of friction, right? Plus I'm going to have my change in EP, which is the same thing as work done by gravity, right? In that case there. And all these three things is W net. And what do I have left on the right-hand side? All I've got left is change in EK. W net is equal to change in EK is the same thing that we used. You could use WNC to get the right answer in that case there, right? So you definitely can use it. Whoever asked that question on TikTok, it's a great question. You can use that. It just means you have to go find the height because you need this height to solve that problem. But how would you find that height? You're very correct. You would then use trig to find that height, and then you can go find the work done by gravity, etc. But if you use your work energy theorem, you don't need to go do that sub-calculation of finding the height. You can go directly to finding the velocity by using W net is equal to change in EK. So that's why I always say, guys, it's very important to look at what information are you being asked for. Also, because in an exam situation, you are pressed for time, right? So number one, you don't want to do any unnecessary calculations. That's the first thing. Number two, you don't want to make your calculations longer than they need to, because the longer your calculation, the more spaces for mistakes you are leaving. So very, very important, but there's nothing wrong with doing it. If that example, if WNC is a formula that you're very comfortable with, and you can do it quicker than you can do W net is equal to change in EK, perfect. You're saving time, which is a good thing. That's fine. So it depends on what you're comfortable with. There's many ways to skin a cat. As long as you pick the method that you are most comfortable with, there isn't one right method. The right method is the method that you can remember. The right method is the method that you can do consistently without making mistakes. That's the correct method. Don't let your friends say, oh no, that's the wrong method, use this method. That's why I'll always say, I prefer using this method, and I'll give you my reason why I prefer it. Because I don't like making extra steps. Extra steps make me make more mistakes. So, but if you are meticulous and you like the extra steps because that's how your brain works, perfect. Use it because you'll be faster at doing that and you can spot mistakes better with a method that you're more comfortable with. I love that question. Thank you, guys. Make sure you keep them coming. Getting very high quality questions today. It's awesome. Okay, that was that one question there. 5.2. Let's still do the rest of them. We have quite a few to go through. 5.3, calculate the minimum average power dissipated by the electric motor to pull the crate from point A to point C, right? Remember, what is power? Power is the rate at which work is done, okay? So what is the minimum average power to be able to do that for 5.3? So to find average power, what do? There's an equation for average power. Average power is P average is equal to F times V average in that case there. So let's quickly go look at that, 5.3. So for 5.3, average power, P average equals force times V average. Okay, now in that case there, how would we work this out? Well, we know what force it is, right? We were told it's 96.8 newtons that the electric motors are flying. So that's 96.8. And then what is the average velocity? Well, average velocity, we can either go distance over time. We don't really know how long it took, right? If I quickly go back and look, they didn't tell us how long it took. But what we do know, I know the velocity at A, I know the velocity at C, right? And it was accelerating constantly. So if I take final velocity plus initial velocity and divide by 2, that gives me an average velocity. So in this case, what I can then do there is I can say, well, for my average velocity, I'll say let me do this. So it's going to be F times my final velocity plus my initial velocity divided by 2. That'll give me an average velocity. So final velocity, we had an answer of, what is the answer? 5.96. So 5.96. My initial velocity was 0, divide that by 2. And if you plug that into your guys' calculators, what you will find is that you will get an answer of, we just have to quickly calculate this, 210 88.46 watts. Remember, power is measured in watts. That's the average power that you will get out of this particular electric motor. Hope that makes sense, guys. Nothing too hectic. Let me check that our Q&A is fine. Nothing in our Q&A. Let's move on to the next question. 5.4. 5.4 says, draw a labeled free body diagram for the crate as it slides down past point B. Hold on now. Oh, so I didn't read the part before. I was like, slide down. What are they talking about? So it says, when the crate reaches point C, the rope breaks. I missed that part. The crate continues moving up the inclined plane, comes to a stop at point D. So it gets pulled from A to C. The rope breaks at C. It goes up to D and then slides down like that, right? So they want to know a labeled free body diagram for when the crate slides down the plane past point B. We can quickly do that. That shouldn't be difficult for us to do. 5.4. Okay, start with our reasonably sized dot. We've got force of gravity, which is always there and acting vertically downwards. We don't have an applied force going up anymore, right? What we will have, though, is we're going to have force of friction coming down. Not coming down, sorry. Force of friction going up because I'm moving down. So when I'm moving down, friction acts against my motion. So my force of friction, sorry for that, will be acting up our incline. And then because we are on a surface, we will have a normal force that's perpendicular to our surface, right? That's our free body diagram in that case there, as the object is sliding down my incline, right? Hope that makes sense there. Let's quickly look at the next question, 5.5, and then we can move to the last topic. I hope you guys don't mind. I still want to do vertical motion with you guys. So if you don't mind giving me an extra 30 minutes, I would really appreciate it. And then we can maybe end at 8:30, just so we've got enough time to do VPM. Physics has got a lot of topics for this time. So 2 hours wasn't enough time, but I know you guys won't mind because you're gaining extra knowledge, which is awesome, and it'll help you guys pass well. So 5.5, draw a velocity time graph for the entire motion of the crate starting from point A until it passes point B again on its motion down the inclined plane. Ooh, this is an interesting one, right? And it's now bringing us into our next topic, which is VPM. But this is not necessarily VPM graph, but it's a motion graph, which is good. Very, very important to go practice motion graphs. Okay, so very important for us to then look at this. Now, let's come and try and do this, right? So when we draw this graph, let me just quickly draw our axes. So, okay, there are axes there. This is time. This is going to be velocity measured in meters per second. And this is time measured in seconds. So our object starts stationary. So my velocity will be 0. And it's pulled by a constant force, right? Pulled by a constant force, meaning it'll accelerate constantly. So if we assume up my incline is positive and down my incline is negative, we can see that it'll start at 0 and then it'll accelerate constantly for a particular amount of time, right? The velocity will increase constantly, gradually up until a particular point. The gradient of that will be equivalent to the acceleration, not 9.8 because this is not free fall, but it'll be a constant acceleration because it's being pulled by a constant force up until a particular point, right? And then at that maximum point, we actually worked out what that velocity would be. That velocity was 5.9 something, 5.96. 5.96 meters per second at its maximum speed. That's at point C, right? Then point C, the rope snaps. But remember, it continues to move up until it hits 0. So the velocity will still be positive, but it's going to be slowing down, right? So as it goes up the incline, it's slowing down. So we expect that my velocity will then come down until it reaches 0 in that case there. We don't know what that angle is. We're unsure, but we know that it will come down until it reaches 0 again, right? And then when it reaches 0 up at the top, it's going to slide down now the incline. And as it slides down the incline, it's going to just sort of keep going down. And then at that point there, we'll have, this thing will keep sliding down the incline in this case here I'm trying to think about if that gradient will be exactly the same. So let's quickly think about this. When I'm going up, I've got gravity pulling me down and I've got friction pulling me down, right? So I've got two forces pulling me down, slowing me down. When I go down, I've got gravity pulling me down, but friction is slowing it down. Okay, which means we must actually show this. It's very important. The gradient for the next part. So let me try and label this thing according to the spaces. So we've got A at the bottom, B, C, D, right? So when we come back to this, here's A, right? And then through time, at the top where the cable snaps is going to be C. Then it hits the maximum height, the top of that incline, which is D, right? So when it gets back to zero, maximum height, that is D. And then somehow it's going to slide back down to point B, right? So please make sure here that the gradient of this last part is not as steep as the first part. Let me explain again why, right? From C to D, you're moving up, right? The forces that are slowing you down is both gravity and friction. So you will have a greater net force from C to D because you've got two forces acting in the same direction or similar direction. Gravity and friction are both pulling you down. Bigger net force, bigger acceleration. Your gradient must be bigger because the gradient of a VT graph is acceleration. So CD must have a bigger acceleration than DB. DB will have a less steep gradient because you have friction pulling you down. I mean, gravity pulling you down, but friction pulling you back up and slowing you down. So you're not accelerating as fast during D to B as you are from C to D. So that kink is important. If you drew a straight line from C all the way to B, you would lose marks in this particular one. So I hope that makes sense to you guys. Actually, a very lovely question. I love this question and how they put it out there. Yeah, it's a very great question. Okay, that brings us to the end of work, energy, and power. And we're going to then, because we've been in the space of motion and motion graphs, we're going to jump straight into VPM. I'll wait for any questions in the chat or in the Q&A before I move right along. I'll give you guys 2 minutes to ask any questions you've got. Keep the very high quality questions coming. I've been enjoying them in this session. I'll give you guys 2 minutes to put your questions down if you've got. Gabeto says, please go back to 5.2. Gabeto, you need to tell me exactly what about 5.2 you didn't understand. So I'll put the question up and then I'll give you a chance to reword your question and tell me exactly what about it you didn't understand, not just go back to the question. Okay, I've got the questions there. So Gabeto says, I understood. I'd just like to take a screenshot. So I must give you the solution for 5.2. I'll do that for you just now. I hope this is visible. If not, what I'll do is I can zoom into the different parts of the question. Otherwise, Theo, is there a way we can send everyone the notes from this lesson? We've got what? We've got the... Oh, Theo, we've got a WhatsApp community. Can we share a link of that in the chat? And then if they join it, I'll share the notes in the WhatsApp community. I think that would work.
Okay, Ernest.
Okay. I don't know how, if I don't know if it's possible to share the WhatsApp community in the chat. Let's share it both on TikTok and on Zoom. And then I'll share the notes from this lesson in the WhatsApp community. And then at least everyone can see the solutions as I work them out. And then you'll also get access to these notes if you join our WhatsApp community.
I'm working on it now.
Okay, thanks, Theo. Awesome, guys. And then let me see what other questions there. Passing through D. Not sure what that means. Oh, someone says, why can we not draw a continuous line from C to B passing through D? I'll quickly go back and reiterate that one. So remember, let's quickly go back up to the diagram. So what they said was, this object starts at A, right? Starts from rest at A, and then it goes up, up to C. At C, the rope breaks. Something goes wrong, the rope breaks. It already had momentum. Remember from the first topic, we had mass, we had velocity. Momentum will keep it going up to D, where it's going to turn all its kinetic energy into potential energy. Now it's going to hit maximum height. Velocity equals 0. Then it'll slowly then turn all of that potential energy back into kinetic energy by sliding down. So the important thing here, we're comparing C to D and D back to A. I want you to compare the free body diagram of C to D to that of D to B. It'll be the same free body diagram. So from C to D, the forces here, we're moving up. So the forces acting against me, we have gravity acting against me. We also have friction acting against me downwards. So I've got two forces acting against me from C to D, which means if you compare that from D to B, when I'm moving down, right? There, I've got friction moving up. And I've also got gravity moving me down. Now, in that case there, the bigger net force is from C to D. My F net is bigger here because I've got two forces in the same direction. Versus from D to B, the forces are acting against each other. My net force is smaller. So your bigger net force will lead to a bigger acceleration. We've got a grade 11 lesson, I think, coming tomorrow. Grade 11 physics is tomorrow, and they'll be covering Newton's laws. So I recommend all of you, I know you're in grade 12, go watch the grade 11 lesson tomorrow because they're covering Newton's laws, which sometimes those topics will come up in a grade 12 exam. Everything you've done in grade 10, 11, and 12 comes up in grade 12. So watch the grade 11 lesson. It's going to be useful for your exam that you're writing again now in term 2. It'll give you Newton's laws access. And then you'll see how then the bigger net force will give you the big acceleration. And because of that, when you're looking at your VT graph, the gradient of a VT graph is equivalent to my acceleration. So my gradient equals acceleration. So CD needs to have a bigger gradient than D down to B. And that's why that is the case. Hope that makes sense to you guys there. Thank you, Theo, there for posting the link to our channel there on WhatsApp. So that channel will just be for learners who need help with any maths and science-based stuff. We'll post links to stuff. We'll post the lesson recording. So please join it. You're welcome to share that community with your friends, and we'll post. So I'm going to post the lesson notes for this lesson on that channel as soon as this lesson is done. Okay. Let me just make sure that we've got everything there. How do you join the WhatsApp community? They put the link there. So just click that link and then it'll let you join the WhatsApp community. And then I'll post my lesson notes on that WhatsApp community as soon as we're done. Thank you for that, Theo. Okay, awesome. With our last 20 minutes, I'm going to try and quickly cover vertical projectile motion. I'll try to be very quick with it, right? But thank you guys for your patience and sticking around with me. As usual, we start with some definitions. So again, what is a projectile? A projectile is any object in free fall, right? What do I mean by free fall? Under the influence of gravity only, right? Only Fg acting on the object. So which means the free body diagram of anything in free fall looks like this. No friction, no applied force, no normal force, none of that. It's just an object freely floating around or moving by the effects of gravity only. Okay, free fall, when the only force acting on the object is gravity, the acceleration is the rate of change of velocity. Of anything in free fall, it'll always be g, which is 9.8 meters per second squared, right? And then the displacement is how far the object is from the reference point, right? That's the displacement you're dealing with in that case there. You'll often see me refer to it as delta y. Some people write delta x, but my brain says y is vertical, x is horizontal. So vertical displacement, I write it as delta y, but delta x, they still give you marks for that. All right. Right. Then there is another awesome video to watch about this. I'm going to quickly share it with you guys. Give me 2 seconds. So if you go to our YouTube, right? So go to YouTube. On YouTube, search for the learning space, ZA. When you get there, there's our page, the learning space ZA, right? And when you're at the learning space ZA, you'll see lots of videos that you can see there. So as I told you guys, on our TikTok, everything else, you'll see videos that we actually have shot and shared in the last few months. So you'll see some videos by me, by Hannah, by Tsapang, lots of videos that we are putting there. Find this video it's called Gravity. This video is very, very important, right? Because this video here, I won't play the video. It's a little bit long. It's about 12 minutes. But if you are a little bit unsure about vertical projectile motion, it will take you through the scenarios. So I'm going to take you through the scenarios now very quickly. This video takes you through this in a little bit of a fun way. Our team went out to bounce in Johannesburg in Fourways, and we were playing around at bounce at this trampoline park, and we were exploring the different ways that vertical projectile motion comes into life when you go to bounce. So it was quite a fun thing. So watch this video. Like I said, the learning space ZA on TikTok, and then you're going to look for this video that says vertical projectile motion fun at bounce. It's the picture is this one here that says it's called Gravity. Really great video with Tsapang, giving us amazing acting skills. I know he's not watching this lesson. He'd cringe if he heard me say that. Okay, let's go back to our lesson, right? So the scenarios, you'll see that video goes into detail about these scenarios. So scenario number one, we're looking at an object that is dropped, right? What does dropped mean? A dropped object is one that starts off with a velocity of 0 and accelerates downwards from there. Note, in all scenarios, acceleration is 9.8 meters per second squared downwards. Always. Not sometimes, always. Even when the object is moving up, the acceleration of 9.8 meters per second per second squared downwards. Always. At maximum height, when my velocity is 0, acceleration is 9.8 meters per second downwards, always. Are we together? The next scenario is an object that is thrown down. So if it's thrown down, that means my initial velocity is not 0. It's bigger than 0, right? So if an object is thrown, don't assume VI is 0. It's not 0. Very, very important. Okay. Then there's one that's thrown up or launched up, right? So we can see velocity at A is not 0 because it's thrown up. It's got an initial velocity. What's important though, maximum height, velocity will always be 0, right? Okay. Another one, velocity at A going up is equal to the velocity at C going down. The velocity at the same elevation will be the same. So if this is 10, that'll be minus 10, for example. All right. And the time taken for an object to go from A to B, so the time going from 1 up is the same time taken to come down again. If this is 2 seconds, that is going to be 2 seconds. That's very important to note. Then you have an object that's launched from a particular height. It's launched from A up to B, down to C, or up all the way down to D, right? Whatever the velocity was at A, so if you draw a vertical line like that, the velocities on that vertical line will always be the same, right? Very important. Apologies, my laptop battery is low. I need to charge it before it dies on us. Give me 2 seconds. Just want to grab my charger. Don't worry about the noise. I didn't die. I just dropped something. Okay, let me just try to keep going, and hopefully this is gonna manage me through the session, or I'll charge while you guys are doing the example. All right. Then the other scenario is when something is dropped from a moving object. The cool thing is, guys, please watch that video. I'm going to post a link of that video in the chat because we actually did this and we managed to actually make it work, right? Where we managed to show people that this actually works. I'm going to go to that video and I'll show you very briefly, right? But you must watch the full video. It's really enlightening, right? That whenever you drop an object from a moving object, for example, the balloon is going up at 5 meters per second, and the object is dropped in the balloon, it means the initial velocity of that object will be the same as the initial velocity of the balloon. If something is moving up and it's dropped, it will initially move up, not down. It'll go up, hit maximum height, then it'll go down again. I'll try and show you guys in that video that just that part, and then you guys can watch the rest of the video yourself, right? Okay, there's a part in this video. So you'll see what you'll see in the video, right? You'll see the object. So in this case, a ball is going to be released. So you'll see someone on screen, Motel was bouncing on a trampoline. As she's bouncing, on her way up, she will release the ball. And notice how the ball is going to go up before it comes down, just because it has the same initial velocity as she had on her way up, right? So I'll play that quickly for you guys.
The object will momentarily continue in the direction of the object that was already in motion. In this case, the object continues to go up and then it will reach a velocity of 0 meters per second and then go down. At the instant that it hits the ground, the object has attained.
So you can see there in that video that the person had the ball and they started at a particular height. They were on their way up when they released the ball. So they dropped the ball, but they were moving up. The ball didn't just go down. If I play the video again,
momentarily continue in the direction of the object that was already in motion.
It reaches
In
a
this
maximum
case,
height, and
the
then the
object continues to go.
So it's pretty fun. That's why I said go watch the video. It's very cool, where we actually put our lives on the line for you guys, right? So let's quickly go back and finish off this lesson. So the last scenario, as I said, if an object like a hot air balloon is moving up, right, and then an object is dropped from that object that's moving, the initial velocity of the object will be the same as the initial velocity of where it was released. And then it'll go up and then maximum height and then come down again. There's a question quickly that I see there. Okay, Zeliwe, I see your question there. Let me finish up with this, and then I'll come back and I'll address this right at the end, right? Okay, so those are our scenarios that we're dealing with. And then quickly, let's go through some quick hints and tips with VPM. So with VPM, right, the important thing is to always remember data, direction, and diagram, right? So meaning, note the data that's always been given to you guys there. There's a diagram that you need to draw, right? The diagram is what I refer to as the milestones diagram, right? And then the direction is important because you're dealing with vectors. Some things go up, some things go down. Pick a sign convention, up and down. Those are very important. So the data is whatever was given, right? So you've got velocity initial, velocity final, acceleration, delta x. And then you'll say, okay, I've got these three known values, this unknown value. Which equation can I pick from my equations of motion that will give me the answer that I want? Remember to indicate positive or negative direction so that you don't substitute the wrong one, okay? Then put a question mark next to a quantity that you're trying to find or don't know the value of. So when you do your diagram, right? So this is the milestones diagram that we refer to. So let's say they said an object is thrown up from the edge of a building, it reaches maximum height and goes down and hits the ground. So you need to draw that. What I always recommend, how to know which points to put there, go read the full question and see what they ask you. So they might ask you, how long does it take for the ball to pass the person again on its way down? Then you know C is there. You know, they'll ask you maybe about maximum height, B is there. They'll ask you, you know, after 5 seconds, what's the velocity? Maybe that's D. And then they'll ask you, what is the speed of the ball when it hits the ground? That could be E. So make the milestones and say, I need information at A, B, C, D, and E. Put those on your diagram. Then you know you need to find important facts. Another reason why this is important is because whenever you're doing VPM, vertical projectile motion, you need to always work between 2 points and don't confuse your values, right? Sometimes when you guys don't put your values, you just do a calculation, VF, VI, VF, VI, and you're going to just end up substituting random values at random places. So what I like to do is I'll draw my milestone, and then when I decide to do a calculation, I'll say, okay, I've got the most information from A to C. When I do my calculation, I'll then say, I'm working from A to C. That way I know anything that's initial must be A, anything that's final must be C. And then you'll put all those values down, right? Now again, choose the direction, positive or negative, and draw it in your diagram. So like there, we said up was positive, down is negative. You've seen me do that in all of my mechanics questions, is draw my sign convention. It's very important to avoid you making mistakes. And then each equation of motion has 3 variables, right? So that means it's 3 pieces of information that are needed to calculate the 4th one. So the equations of motion are valid for a constant value of acceleration. In this case, it's normally 9.8 downwards, right? Therefore, a new calculation must be performed each time the acceleration changes. So in this case here, you're not really going to have changing acceleration for VPM, but if anything else changes, if you need A to B or B to C or C to D, you need a new calculation to do that there. All right. And then finally, when we do the graph, there's a video I did on motion graphs on our YouTube. You guys can go check it out. I'm not going to waste a lot of time on the motion graphs for now. There, I'll go into a lot of detail. It's a lesson recording of a lesson I did on VPM. Go watch that lesson recording, and then you'll get all the detail on how to draw the graphs, from the AT graph to the VT graph to the XT graph. We did some graphs on bouncing balls as well, right? We did a bouncing ball example earlier on, where you can see collision with the ground that's inelastic versus collision with the ground that is elastic, and how that looks different in both cases. We did the inelastic version in the question at the beginning of the lesson today, so that will be useful to you. Okay, we've got 10 minutes left. Let me quickly try jump on this question. 15 marks. We'll hopefully get to do it in time. All right, so let's quickly look at question 3. Question 3 then says, ball A is dropped from rest from the top of a building that's 15.2 meters high. That's shown in the diagram, which is good. After ball A has fallen 3.2 meters there, right? A second ball B. Someone already should know what's happening here. When you've got 2 balls moving, in this particular case, we're going to be dealing with people's favorite simultaneous equations, right? In vertical motion. So after ball A has fallen 3.2 meters, a second ball B is projected vertically upwards from the ground. After a while, the 2 balls strike the ground at the same time. Very important. This is a very important thing for us to note to solve this particular thing. I'm going to go and highlight very important information that has been given to us there. Ignore the effects of air resistance. Then 3.1, define the term free fall. I'm not going to write this one just because we've got time pressure, right? But if you go back to our notes, you'll remember free fall is when only gravity is acting on an object. There's your definition for free fall, when the only force acting on an object is gravity. That is what is defined as free fall. Very important. Let's quickly go back down and do the next question. Question 3.2 then says, calculate the time taken for ball A to strike the ground, right? So in this case here, we need to look at how long did ball A take to strike the ground, and then we're going to go back and look at the diagram. So let's try and do our milestones for ball A. So ball A starts here. I'm going to call this point 1. That's a very weird one. 1. It moves down 3.2 meters later. That's point 2. That's an important point when ball B is released. And then it continues right down to point 3. Those are my milestones for ball A. Ball B, I'll do in a different color. Ball B, right, starts here. Let's call that point 1 for B. there doesn't seem to be a lot of other things. Let's see what they talk about B. The magnitude of the velocity with which ball B was projected. That's what we need to know. And then it's probably just going to go up and then down again. So B will go up, hit maximum height. Let's call that 0.2 for B. And then it will come back down again and hit the ground. Let's call that 0.3. Those are my two milestone diagrams for ball A and ball B. The first one there, the time taken for ball A to strike the ground. What information do we have for 3.2.1? So we know that ball A was dropped. That's very important. What does that mean? It means the initial velocity was 0, right? So the velocity at 1 here, V1 for A is equal to 0. We know that for the acceleration of all the balls, A equals 9.8 downwards, and we need to pick a sign convention, right? So in this case, I'll just pick up as positive and down as negative, right? Meaning my acceleration there will be negative 9.8 meters per second squared, or negative 9.8 downward. I mean 9.8 downwards. Okay, so let's look at what we need there. Time taken for A to strike the ground. We've got the initial velocity. We've got the acceleration. We've also got the delta y, the distance it covers the displacement, 15.2 meters, right? So we can take that and then we can go find the time which this ball takes to strike the ground. So let's quickly try and find an equation that we can use for 3.2.1. Quickly do that. 3.2.1, right, which is 9.8, negative 9.8 because it's downwards. We have the initial velocity, which is 0 because it was dropped. We have the delta y, right? Delta y is the displacement. That is negative 15.2. The reason why I say negative 15.2 is because the displacement is downward. It starts at the top and then it goes down. So my displacement needs to be negative. If you put it as positive, you'll get the wrong answer. And they asked us to find the time in which it takes to do this. And that's what we don't know. That's what we need to be able to find in this problem here. So which equation can we use to solve this? For these values here, the equation I think we can use there will be delta y is equal to, I hope this doesn't bite me in the butt, vi delta t plus half a delta t squared. Solving time with this equation is a little bit of a pain because it means I've got a quadratic and I have to use the quadratic formula. But it works out because my initial velocity is 0. So that whole term will become 0. That's great. Okay. So this whole term becomes 0 because that is 0. That saves us quite a bit. Let's substitute, right? Our delta y, we said, is negative 15.2. That whole term there becomes 0 times delta t plus half a delta t. Sorry, we know what a is. Just plug that in there. Negative 9.8 times delta t squared, right? So we put those values in there. Let's simplify and solve for delta t. So we've got here negative 15.2 is equal to half of negative 9.8 is 4.9. So it's negative 4.9 delta t squared. So delta t squared is equal to negative 15.2 divided by negative 4.9. And then delta t is simply going to be the square root of 15.2 over 4.9. If you plug that into your calculator, you should find that you get an answer of 1.76 seconds. Okay, so now we know the time it takes ball A to go all the way down from 1 to 3 is that 1.76 seconds. Hope that makes sense to you guys. I'm going to move on to the next question so we can try quickly wrap up, right? Okay, that's 3.2.1. 3.2.2 says, calculate the magnitude of the velocity with which ball B was projected from the ground. Okay, so this is going to be one that requires a little bit of work, but I'm pretty sure we can work it out, right? because the important fact there is that set there, right? That the two balls strike the ground at the same time. That's very, very important. They strike the ground at the same time. So let's quickly try and figure that one out, right? So what do we first need to try and figure out for 3.2.2? I actually think we might be able to do this without a simultaneous equation. So 3.2.2, it looked like a simultaneous one. So because we know that they strike the ground at the same time, we need to find now the velocity with which it was thrown up, right? So what we now need to try and figure out, right? So they told us that ball A fell 3.2 meters. After 3.2 meters, ball B was then thrown, right? So in that case there, I'm going to say, well, okay, let's try and figure out how
Apologies, everyone. I think our host is just having some technical issues. Please just bear with us whilst we sort this out. Thank you for your patience, everyone. Please don't leave just yet. He will rejoin. I think his Zoom just kicked him out, but he is definitely rejoining us. Apologies again, everyone.
Sorry, can you guys hear me? Apologies. I think my Zoom just crashed. I don't know what happened. I got disconnected from the session.
Yes, we can hear you now.
Okay, thanks, Taffy. Let me quickly try and rejoin my whiteboard. Sorry, guys, for that. Let me just confirm if you can see my screen.
Yes, we can.
Okay, cool. Thanks. Sorry about that, guys. So we were still at the point of trying to figure out, they told us that ball B, right? So A goes down 3.2 meters, right? And then at this point, ball B gets thrown. From the time A goes from here to there, B goes up and then down and hits the ground. So we need to figure out then, okay, cool. How much time did it take A to go from here to there? We know what the total time is. We just worked that out. So what is the time it took A to go from here to there? Once we know that, we can minus it and find the time from here to there, because that time is how long it took B to go from the ground up all the way back down again. So we need to find the time A covered, the 3.2 meters. That's the first thing. So let's quickly do that together. So we need to find the time, delta T, right? That A covered the 3.2 meters. Okay, we don't know what that is. We're going to try and figure it out. But what do we know? We know that the initial velocity for A is 0 because it was dropped. We know that the acceleration, that looks like a 9, it's meant to be an A. Acceleration is negative 9,8. We also know that the delta Y, right, is negative 3,2 meters. Remember, it's negative because we chose up as positive and down as negative. So that displacement goes down, it's going to be a negative displacement. Those are the values we've got. We need to try and find an answer there. I think the very same equation we used before should help us again in this case, right? Let's substitute it all in there. Delta Y equals VI delta T plus half a delta T squared. I'm not scared of this anymore because I know that VI is 0, so it's going to cancel out entirely. My delta Y in this case is negative 3,2. My VI is 0, delta T plus half negative 9,8 delta T squared. Okay, let's try solve this one here. We know that negative 3,2 equals half negative 9,8 is going to be negative 4,9 delta T squared. Therefore, delta T squared equals negative 3,2 over negative 4,9. And then to get the final answer, we need to square root both sides. And then that'll give us an answer of delta T. When you plug that into your calculator, you should get an answer of 0,81 seconds, right? That's how long it took ball A to move from where it was dropped down 3.2 meters. Okay, now that we know that, we need to find the time it went from there to there, which is the same time B went up and down. Pretty easy, nothing complicated. Let's quickly do that. So to find the time, right? So find the delta T of B, we know we're going to take the original time, that 1.76 seconds we calculated in the previous question there, minus 0,81 seconds that we just calculated there. And that'll give us the time that B was in the air. And that should give you 0,95 seconds. That's the delta T for B's entire motion. Now we've got the time that B was in the air for. And that's pretty chill, because now we know that it goes all the way up, it comes all the way down, right? Now here's a little trick I want to show you guys, right? So let's think about this. I want you guys to post this in the chat. My question is, what is the displacement of B? Right? So B started at 1, goes up, comes down to 3. What is the displacement of B? Quickly put that in the chat. If B goes from 1 on the ground all the way up maximum height and it hits the ground again, what will its displacement for the motion be? I know we are over time, I'm almost done. Thanks, Gabito, for your answer. I'll give you guys 10 more seconds to try and give me an answer for the displacement for B. I'll give you a hint. Remember what displacement is: the shortest distance between start and finish. What is the displacement? Shortest distance between the start and the finish. It starts on the ground, goes all the way up, comes back to the ground. 5 seconds, 4, 3, 2, 1. So remember, if I start on the ground and I go up and I come back down, I started here, I ended here. What's the shortest distance between the ground and the ground? 0 meters. So that makes sense. 0 meters is my displacement, right? Because it ended off exactly where it started. And that's the trick to how we're going to solve this particular one here, right? So when we do this one here, we come and we try and solve the values for B. We know the time was 0.95 seconds, right? We now also know that here, our displacement, our delta y for B's motion was 0 meters, right? It ended up exactly where it started, okay? What else do we know about B? We know that the acceleration is negative 9.8. So we've got that, and we need to find the initial velocity, right? So the equation to use here, got delta y, vi, a, delta t. It's going to be the exact same equation we've been using the entire question, which is fine, as long as it works, right? So we've got delta y is equal to vi delta t plus half a delta t squared. Our delta y is what? 0, right? So we know that this is going to be 0 equals vi is what we're trying to solve. My delta t we got up here at 0.95. We will substitute that in there. So that's 0.95 plus my acceleration, negative 9.8, and my delta t squared, 0.95 squared. And then I just need to solve for vi in this case here. So vi will be equal to negative half into negative 9.8 times 0.95 squared, right? And then I need to divide everything by 0.95. In that case there, okay. And then if you've got that, what you should find is you will end up with an answer vi of, so when you solve this, 0.95 squared divided by 0.95, that cancels that, this negative cancels that, and then you basically have 4.9 times 0.95. When you put that in your calculator, you should have 4.66 meters per second. And what was the question asking for? It was asking for the magnitude of the velocity. I don't need to give a direction. That's all they need. Perfect. And then finally, as we wrap this up, on the same set of axes, draw the position time graphs to show the motion of both balls A and B from the instant ball A was dropped until the time it reaches the ground. Take the ground as the 0 position, label the graphs A and B, right? Clearly indicate the following on the graphs: the starting time for each ball, the initial position of each ball, and the time when the ball strikes the ground. So this is a pretty easy one to do, right? Because a displacement time graph looks like the motion of that object, right? So let me draw my axes quickly. Here's my y-axis. Oh, come on. Here's my y-axis. This is going to be my position, x measured in meters. And then this is my x-axis there, time measured in seconds. So let's start with A. I'll draw A in purple. A was launched from a height of 15.2 meters and it was dropped. So if this is 15.2, A will simply just go pew, not like that. It'll kind of just do that, right? And then on the time, I think the original time it took was 1.76 seconds. Yes, it'll land here at 1.76 seconds. B was launched after A. How long after? It took 0.81 seconds before B was launched. So at 0.81 seconds, right? So somewhere there at 0.81 seconds, B was launched. We don't know what the maximum height was. We don't need to know it for this case here, but we know that it ends at the same time that A ends. So literally, boom, just like that. That's what B does. And then we need to label the graphs. This is graph of B. This is the graph of A. Super simple, nothing hectic. That's how it's going to look. Okay, hope that was easy enough for you guys. Thank you so much for staying almost an extra hour for the session. We will have the recording up on our YouTube. I really appreciate your time. You guys are gonna, yeah, we have the science paper 2 on. Taffy, quickly remind me, on Wednesday.
Yes, that's correct. It's on Wednesday.
Okay, cool. Awesome, guys. Thank you for sticking it out this long. I know there's a very long lesson. See you guys for chemistry on Wednesday. Tomorrow we've got the grade 11 session, if I'm correct, Taffy.
Yes, that's correct.
Okay, grade 11 physics. So if you need revision on, you know, your Newton's laws, that kind of stuff, that will be pretty useful for you guys to check it out. So I'd recommend it if you guys want to just get revision on those things there. But other than that, guys, I will take no more of your time. Please go have an epic rest of your evening. I'll see you guys on Wednesday. Cheers. And then you'll have a different presenter for tomorrow and the extra time you guys spent here with us. Have an awesome evening, guys.